Tomorrow's demo is going to be on the Coriolis inertial force. And so to illustrate that, I've got this 2 by 10 by 10. And then I got this solid caster that takes, I think, about 1,500 pounds, 1,000 to 1,500 pounds. So I'm going to cut the wheel off of that, basically use the base like an industrial lazy Susan. All right, all we have to do now is finish bolting it down, and then it's ready to roll.
Coriolis force or effect determines what happens to all fluids and gases. So everything from the oceans to the winds to even what's going on in this room to flushing a toilet all gets deflected depending on if you're in the northern hemisphere or in the southern hemisphere. So this is our North Pole. These guys are our equator. He's going to be sending a water current up to the North Pole. Okay? So this is why they're wearing the hard hats. So let me know if we're going too fast here.
Speed it up.
How's that?
I mean, we're spinning in a circle, so.
All right. So Will, when you're ready, I want you to throw that ball straight towards the North Pole.
Just go straight?
Yep. Whoa, what just happened there? Now you can try it. Because the faster you can spin, the stronger you'll see this Coriolis force. Is that good?
Yeah, I guess.
All right. When you're ready, I want you to throw that ball towards Will. What just happened? Wasn't that strange? Here you go.
This side of the board.
See it again. So which way is it getting deflected? To the right or the left? So let's see it straight out again.
Straight over?
So is that right or left? You guys want to see it again?
I don't know how much longer we can do this.
Come on. Okay, straight out. You guys pay close attention to how it's deflected. Was that right or left? To the right. This is in the northern hemisphere. Okay, now let's correct. Oh, you guys are happy.
Jesus Christ.
Now we're going to flip it. Now we're going to look at the southern hemisphere. You guys ready for this?
No.
Come on.
No way was I ready for this.
Will, you're filming too. You got to keep your head up.
No, it's a little hard.
Okay, now you guys watch. Which way does it deflect when we're talking about the southern hemisphere?
Are we throwing it straight?
Straight out. Was that right or left? It was left. Did everybody see that? All right, let's do it again.
Oh, God.
Here we go, Will.
Why?
Here we go. Straight out, Will.
Straight up? All right.
Straight out. Everybody see it deflect to the
I
left.
feel like they got the idea.
So that explains all of our air and water currents. Give a round of applause. Our Earth from the top. This is our North Pole. And then our Earth from the side. And this is our equator. Everybody can see that okay? So which way is the Earth rotating? Clockwise or counterclockwise? What do you say? Counterclockwise. So it's rotating that way, isn't it? Or it's rotating that way. Fluids and gases are not attached to the Earth. And so they're going to be a little bit behind whenever the Earth is doing a motion. And so I was talking about, in our demo showed, that if there's something, either a fluid or a gas, and it's at the equator, how fast is that traveling? It's on the board. How fast is something on the equator traveling? About 1,000 miles per hour. That's pretty much hauling ass, isn't it? What about if you're sitting on the North Pole, how fast do you travel? Zero, right? You're just rotating on the North Pole. And so that in itself is the key to this whole Coriolis effect. And so if you're something at the equator, you're traveling both this way at 1,000 miles an hour, and then you want to head north to the pole, so you're going to head that direction. And so that direction is going to be a combination of the two, isn't it? It's going to be forward and to the right. And so the resulting direction is going to be that arrow right there. Likewise, if you're up here at the North Pole, and you're a fluid or a gas and you want to head towards the equator, you're not traveling any speed, right? So your only direction is going to be straight south towards the equator. The problem is you're heading south towards the equator, the ground is actually speeding up below you, isn't it? The ground is going to be traveling, as close you get to the equator, it's going to be traveling up to 1,000 miles an hour. So the ground is going to go past you. As a fluid or gas, you're not connected to the earth, and so the ground is actually going to spin past you, and so it's going to be almost like a negative resultant arrow in that direction, and so your path will again be to the right. Does that make sense for everybody? And so we saw that in the demo. When they threw the ball, them being out at the equator, were traveling the fastest they possibly could, and as the ball left the equator and started heading towards that north pole in the middle, it diverged to the right if we spun them in the counterclockwise direction. Then I said, let's do the south pole, so I spun them in the clockwise direction, because if you look at it relative to the south pole, if you're looking up, it's clockwise, isn't it? And so when we draw these arrows in the south pole, if things are gonna, or in the equator, if they're gonna head south, they're gonna do basically just the opposite, isn't it? Because when you're looking up from the south pole, everything deflects towards the left, like that. When we finally apply our wind directions, and these are the wind directions at the surface of the earth, remember these are giant tubes of spinning air, this arrow is going to deflect since it's heading from the north pole towards the equator. It's going to do that deflection towards the right. Likewise, in the south pole, it's going to do the deflection towards the left. And so that's everything. That's wind currents, that's water currents, that's everything on the earth because it's not attached. And you're going from an extremely fast spinning environment to an extremely slow spinning environment.